And now we can go to the solutions of the quantum mechanical problems using Schrodinger wave equation. Am I audible?
Yes, sir.
Yes, sir.
Okay. So, in order to gain some insight into the methods of approach of quantum mechanics as well as some of the interesting prediction of the theory, let us find out the eigenfunctions and eigenvalues of some illustrations, some illustrative one-dimensional problems. In these examples, the potentials and wave function vary only in one direction, that is in x-axis, which we choose to be x direction, and the time dependent Schrodinger equation to be considered here as I h cross del psi by del t is equal to minus h cross square by twice m del square psi by del x square plus u psi, and the corresponding time independent Schrodinger equation has the form minus h cross square by twice m del square psi by del x square plus u psi is equal to E psi, where E is the energy operator and U is the potential operator. And if you write it in this form, that is del square psi by del x square twice m by h cross square E minus u psi is equal to 0. And it is a second order differential equation whose solution depends on the form of potential function u. Okay. The complete solution can be obtained only if the boundary conditions satisfied by psi are known. Okay. What are the boundary conditions? So far we have encountered two classes of wave functions. Wave function representing wave packets that are well localized and for which normalization integral converges. And the second class is traveling harmonic wave represented by the function e to the power I k dot r minus omega t, in which normalization integral diverges. And the wave function belonging to the former class represents particles which, if free, are initially localized to a particular region of space by external forces derived from U, and this describes the bound states. The wave function belonging to the latter class represents particles which are not localized. They travel through the region under consideration from one distant part of space to another. These wave functions are useful in describing the scattering of particular particles by field of force. In either case, wave functions are bounded at great distances in all directions, that is psi when x is equal to plus minus infinite is equal to 0. And what is the continuity condition? This equation which I have described you now, that psi double dash plus twice m by h cross square E minus u psi is equal to 0. And this is a second order linear differential equation. It has two linearly independent solutions for any energy capital E. Thus, if U is finite everywhere, whether or not it is continuous, a knowledge of the wave function and its derivative along the surface makes it possible to integrate the equation. This helps in finding the wave function at any point. And the probability of existence of a particle cannot be partially discontinuous. Therefore, psi must be continuous across the boundary where U changes abruptly. We have to further specify the boundary condition on the first derivative of psi. For the purpose, we consider a very small region of space del x localized at the boundary. And the change in psi dash is equal to d psi by dx over this region is given approximately as del psi dash is equal to d psi dash by dx multiplied by del x is equal to psi double dash multiplied by del x. And this is equal to twice m by h cross square u minus e psi, and for a given particle, twice m by h cross square is a constant quantity. M is constant and h cross is constant. So twice m by h cross square is a constant quantity. And your u and e have finite values and psi is also finite. So your del psi dash tends to 0 as del x tends to 0. So psi dash is equal to constant as long as u is not infinite. Then we say that psi dash is continuous across the boundary. So we can summarize all these concepts, and we can say that the wave function psi is finite, continuous, and single valued, and The first derivative of psi is finite, continuous, and single valued at all points where u is finite. And these requirements also have the consequence that the position probability density for a physical system is finite, continuous everywhere. Then let us discuss general features of solution of one-dimensional problem. The study of one-dimensional problem is significant because of two reasons. First, many real problems encountered in atomic, molecular, nuclear, and solid-state physics, which are three-dimensional, can be reduced to equivalent one-dimensional problems. Secondly, various aspects of bound states and free states of a system can be understood easily from the study of one-dimensional problem. Exact analytical solution of the one-dimensional time-independent Schrodinger equation can be obtained only for a limited types of potential U. Before going to specific example, we consider some qualitative features of the solution of Schrodinger equation in a general one-dimensional potential. And the time-independent Schrodinger equation for a particle of mass m and energy E moving in a one-dimensional potential U is d square psi by dx square plus twice m by h cross square E minus U psi is equal to 0. So your d square psi by dx square is equal to twice m h cross square U minus E psi. And the nature of the solution is dependent on the relative values of E and U. So if U is greater than E, the RHS is positive. So d square psi by dx square has the same sign as that of psi. This implies that psi is convex to x-axis as shown in the figure. If U is smaller than E, the RHS, the right hand side of the equation is negative, and hence the sign of d square psi by dx square is opposite to that of psi. And psi is concave to the x-axis or is towards x-axis as shown in the figure. Now you see, depending on the relative values of E and U, the solution psi may be convex in one region and concave in another region. But the boundary conditions demand that the wave function be continuous and be continuously differentiable. That is the first derivative is continuous. So the general solution is a continuous curve satisfying the boundary conditions. We mention the following general conditions without proof of one-dimensional motion. These features will be illustrated with specific examples of potentials of appropriate places. If E is smaller than U, the nature of the solution is as shown in the first figure. And they diverge as x tends to plus minus infinite. Such a solution is not admissible if E is smaller than U everywhere. However, if E is smaller than U in some region and E is greater than U in another region, then this solution can be connected continuously. If E is greater than U and E is greater than 0, the solution is as shown in the second figure. This corresponds to free states with wave vector k is equal to twice m root over of E minus U by h cross. And the wave vector and energy can have any continuous value. And the energy spectrum is continuous. And if E is greater than U and E is smaller than 0, the solution are as shown in the second figure. This corresponds to bound states with negative energy. The classical motion is periodic and the energy and wave vectors are constant to have some specific allowed values. That is, there exists at least one bound state. The spectrum of bound state is discrete. The energy eigenvalue are non-degenerate. And if multiple bound states occur, they are alternatively symmetric and antisymmetric with increasing energy. So we have some problems. The finite potential well or bound state and its solution. The graphical solution and energy eigenfunctions and that of infinitely well. Then linear harmonic oscillator or simple harmonic oscillator problem and its solution. Then the energy level diagrams. Then probability density, nature of probability density. Then your hydrogen-like atom and its solution. radial waveform function, different states, and the quantum numbers. Okay. So let us have these specific problems in the next class, or shall I continue? Shall I continue the application, or we shall have it in the next class? Anybody?
Continue, sir.
Okay. Because I think one example will not be completed within the limited time.
Okay, sir. Then next class.
Before that, let us have this angular momentum operator in Cartesian coordinate, which can be completed. Quantum theory of hydrogen-like atom. So the angular momentum operator can be derived from linear momentum operator using the following relation: L vector is equal to r cross p, where L is equal to xi cap plus yj cap plus zk cap, and p is equal to pxi cap plus pyj cap plus pz cap. And the real vector will be written as I cap, j cap, k cap, x, y, z, px, py, pz in a matrix. So your Lx cap can be written as y cap, pz cap minus z cap, py cap. Ly cap will be written as z cap, x cap minus x cap, pz cap. And Lz cap will be written as x cap, py cap minus y cap, px cap. And you can have your Lx cap is equal to I minus IH cross del by del z minus z into minus IH cross del by del y. This is equal to minus IH cross y del by del z minus z del by del y. Similarly, Ly cap can be written as minus IH cross z del by del x minus x del by del z. And similarly, Lz cap can be written as minus IH cross x del by del y minus y del by del x. And the angular momentum operator can also be expressed in spherical polar coordinate system, where your x is equal to r sine theta cos phi, y is equal to r sine theta sine phi, z is equal to r cos theta, and your r is equal to root over of x square plus y square plus z square, and cos theta is equal to z by r, and tan phi is equal to y by x. So by differentiating, you can have your del by del z is equal to cos theta del by del r minus sin theta by r del by del theta. And similarly, dy by del x is equal to sin theta sin phi del by del r plus cos theta sin phi by r del by del theta plus cos phi by r by sin theta, cos phi by r sin theta del by del phi. Okay. Similarly, you can write del by del x is equal to sin theta cos phi del by del r plus cos theta cos phi by r del by del theta minus sin phi by r sin theta del by del phi. And your components Lx of orbital angular momentum in terms of the spherical polar coordinate system can be written as your Lx cap is equal to IH cross sin phi del by del theta plus cos theta cos phi by sin theta del by del phi. And similarly, Ly and Lz can be written as spherical polar coordinates as Ly cap is equal to I minus IH cross cos phi del by del theta minus cos theta sin phi by sin theta del by del phi. And your Lz can be written as your minus IH cross del by del phi. And the square of orbital angular momentum can be written as L cap square is equal to Lx cap square plus Ly cap square plus Lz cap square. Okay. Then by using these, you can solve Schrodinger equation for spherically symmetric potential, and we shall discuss it in the next class. Thank you.
Thank you, sir.
Thank you, sir.